In this problem, we consider a uniform rod. The two endpoints are D and B. And as you can see, I have drawn it a little bit slanted because this rod is leaning against a wall. So here's a wall at this point here, which I can call C. The rod is resting on the wall, and the lower end B here is held by a string that is attached to the wall at the point A. So this string here is under tension, and I will call the tension of the string T. At the center of mass of the rod, there's also the weight of the rod, which I will just indicate with the letter P, and we assume that P is known. So this length here is half of the length of the rod, which I will denote with the letter L. So this length here is L over 2, the length of the rod divided by 2. Let's also assume that the height of the wall is h, and this angle here is alpha. So alpha, h, p, l are given. Since there is no friction and this rod here is just leaning against this wall here, the reaction of the wall can only be perpendicular to the rod itself, and I will call this reaction RC. There can be no component that's directed along the rod, because otherwise there would be friction, and we have no friction in this problem. At the point B, we can also have a vertical reaction, RB, because this rod is also in contact with the ground here, so there can be a reaction there. And we assume that the rod is at rest. So it's stable, leaning against the wall, attached to a string, and the rod is at rest. Therefore, the sum of all the forces acting on the rod must equal 0. And also the moments, calculated with respect to any point. What we need to find here is the reaction RB, T, and RC. So we have three unknowns. Let's start from the equation of forces. In this case, we are on a plane. So the sum of all the forces along the x-axis, and let's assume that this is the x direction, must equal 0. The algebraic sum. So let's take this direction as the positive one. Since this angle here is alpha, RC times the cosine of alpha is the projection of RC along the x direction. This force minus the tension of the string should equal 0. As you can see, T goes in the negative direction of the x-axis, and these two are the only forces in the x-axis. Then on the y-axis we have RB, and let's take this as the positive direction for the y-axis, plus RC times the sine of alpha, so this component here, minus the weight of the rod, equals 0. And finally, the equation of moments. We can calculate moments with respect to the point B. In order to calculate moments, in this case, we can do it very easily like this. For example, let's take P. We are interested in the distance of this line to the point B. So we have to calculate this distance here and multiply the distance by P. So that distance is just L over 2 times the sine of alpha times P, and the force P generates an anti-clockwise moment. It's quite easy to visualize. And let's assume that anti-clockwise moments are positive, so we put a plus sign here. The forces RB and T generate no moments, because the distance from the point B is equal to 0. Whereas the force RC generates a moment with a negative sign, because it goes clockwise, and we need to find this length, which is the distance from the force RC, and this length here is just h divided by the cosine of alpha. So we have minus h over cosine alpha times RC equal to 0. From the last equation, we can find RC. RC is just equal to L divided by 2h times P times sine alpha cosine alpha. Or if you want, you can rewrite a more compact expression, because the product of sine alpha cosine alpha is just sine of 2 alpha divided by 2. So we get RC is just equal to L divided by 4h times P times the sine of 2 alpha. And once you get the expression for RC, you can obtain the other two forces very easily. For example, from the first one, you get that T is equal to RC times the cosine of alpha, and we have obtained RC from this equation here. And finally, we also get RB from here, because RB is equal to P minus RC sine alpha, and that's the solution.